Now, let's look at this interesting numerical which helps us in computing the adjustment coefficient for uh, excess of loss reinsurance along with a proportional reinsurance, just to compare in which mechanism the probability of ruin is much lesser. Right, it's an interesting numerical from that standpoint. Let's see how it is working. Claims occur on a portfolio of insurance policies according to a Poisson process. Okay, so the number of claims are following a Poisson process with a parameter some lambda. Individual claim amounts are either 1 with a probability of 0.7 or 8. So one of these two values are occurring as claim with a probability of 0.3. The insurance company uses a premium loading of 60% to calculate the premium and buys excess of loss reinsurance. Retention limit is M, where M is lying between 1 and 8. And the reinsurer is charging a load, is using a loading of 120%. Fair enough. Calculate the smallest value of M that the insurance company should consider if it wishes to expect to make a profit on the portfolio. First of all, what is the expected claim amount? The expected claim amount from the insurer's standpoint is expected value of n times the expected value of x. Expected value of n, it's a Poisson distribution, so lambda is the expected value. Then expected value of x, this is how the x is coming out. So the expected value of x for me comes out as 0.7 times 1 plus 0.3 times 8. So this is working out to somewhere around 2.4 plus 0.7, it's coming out to 3.1 lambda. So the expected claim payout is around 3.1 lambda, and on the top of it we are talking about a 60% loading as a part of the premium collection, which works out to 3.1 times 1.6, which will give me around 4.96 lambda. So the expected the expected premium is 4.96 lambda, right? Let me call it expected premium, which is coming out to 3.1 times 1.6 lambda, right? This is coming out to the 4.96 lambda, which is working out as the expected. And now we are saying there is a possibility of a reinsurance. So because there is a excess of loss reinsurance, and that too the retention limit is M. So for this 70%, it's an so now the expected premium or the expected claim payout with the reinsurance, the expected claim payout is becoming, there is a 70% chance that he'll pay 1, because 70% chance of occurring 1, and for that 1 we are not setting the reinsurance limit. But with the 30%, anything that is even if whatever is the M, that is reinsured. So the only possibility is 8 is going to come. So the whatever is the M in that case, that M is the one that is typically being borne by the insurance company up to the retention limit, and 8 minus M would be borne by the reinsurer. So in that case, I am seeing that the expected claim payout is 0.7 plus 0.3 M. So this is the expected claim payout. And from the reinsurer's standpoint, okay, here from the insurers, okay, this is for one single claim, and if I am multiplying it with lambda, that is the for all the number of claims. So we are coming out that with the reinsurance, this is the expected claim payout of the insurer. And now, so from that, from the reinsurer's perspective, if I am looking at expected claim payout, so there is a 30% chance that he is making a claim payout, and whatever is the claim payout, it is 8 minus m always, because 8 is the loss that can occur and m is the retention limit. So 8 minus m. On the top of it, the reinsurer is charging 120%, which means I am multiplying it 2.2. This is for one single policy, so I am multiplying it with lambda. So the expected premium, the expected premium from a reinsurer's perspective is coming out to this number, 6.6 times 8 minus m, right? So 8, or I can keep it like this itself, 6.6 lambda times 8 minus m. That is the premium which the reinsurer will be charging. Now, what is the question? Smallest value of m that the insurance company, if it wants to choose if it wants to expect to make a profit on the portfolio, insurance company is charging a premium of 4.96 lambda. Out of it, let's say it is making a reinsurance premium of 6.6 lambda times 8 minus m, and along with that it has to do a claim settlement of zero point 0.7 plus 0.3 m lambda. So this, in this entire space, this entire thing should become 0, so I can eliminate the lambda for simplicity. So it becomes 4.96 minus 6.6 times 8. 6.6 times 8 is around 52.8, minus 52.8 plus 6.6 m minus 0.7 minus 0.3 m is equal to 0. So overall it is coming out like 6.3 m is equal to whatever the numbers, 52.8. Oh, this is not 6.6, sorry, this is 0.66. 0.3 times 2.2, this is 0.66. So it is 5.28. So 4.96 minus 5.28 minus 0.7. Right? 5. So this is working out to 6.6 m minus 0.3 m, which is 3.6 m, is equal to 5.28 plus 5.28 plus 0.7, 5.98 minus 4.96, which is 1.02. So m has to be definitely greater than 1.02 by 0.36. Right, this becomes 0.66 m. 0.66 m minus 0.3 m, which will become 0.36 m. So this is 0.36 and m should be greater than 1.02 by 0.36. M should be greater than 1.02 by 0.36, making it 2.83. So only if m is greater than 2.83, there is some kind of a chance that the expected profit exists for the insurer in this case. So that is how I am calculating the minimum value of m so that the insurer can expect to make a profit in this scenario. Then derive the adjustment coefficient equation for the insurance company. Now we know there are two equations. I can use mx of r equal to 1 plus cr, or probably I can use lambda mxr equal to lambda plus, I'll take the total premium lambda into 1 plus c if I'm having the total premium times the r. Any one of them I can very well use, right? So for simplicity, I'll try out the first one, mx, so the moment generating function with respect to r. Now look at the moment generating function for this kind of a scenario. Okay, there is a 70% probability, so 70% probability of a claim of 1 and 30% probability that the claim is m. So this is what is becoming the moment generating function for the same. So this is the moment generating function on the left hand side, and I am having 1 plus the c. The c is the net the net premium amount, or the typical c is the net premium amount that would be that is getting paid. I mean, when we're going with the reinsurance, we are talking about, I mean, after taking the reinsurance, what is the net premium that we are looking at? So it is 4.96 lambda minus of 0.66 times 8 minus m. So instead of lambda, I am taking the entire thing to be r. So 4.96 minus 0.66 times 8 minus m r. So this can very well be simplified, and I am also given that m equal to 4. So this is working out to 0.7 times e power r plus 0.3 times e to the power of mr is equal to 1 plus 4.96 minus 0.66 times 4, 0.66 times 4 times r. So we'll try to look at now. M is also 4, right? So okay, now let me take some value for r. Let's say I'm taking it as 0.1. Now the LHS for me is zero point 0.7 e to the power of r. So 0.7 times e to the power of r plus 0.3 times e to the power of mr. M which is 4. Zero point 0.3 times e to the power of mr. So making the left hand side is 1.22 and the right hand side is becoming 1 plus 4.96 minus 0.66 times 4. So this much r is what is coming out on the right hand side, or probably 1 plus, I have to take it separate. So this is 1 plus 2.32 r. So this has to become 1, so this much times r plus 1. So this is 1.232. Now this is where I'll do a trial and error work to try to minimize the error altogether and try to arrive at a proper value of r in this case. So I can go on a trial and error basis, but here I'll try to use this gold seed to understand. And once I'm doing it, yeah, I got Okay, if I had taken some value of R, it is coming out as, so on a simplification, so this is zero point 0.7 times e to the power of r plus zero point 0.3 times e to the power of 4r, and the right hand side is coming out to 1 plus 2.32 r. So that is what is coming out to 0.232 plus 1. Okay, so this value has to be actually, so probably if I'm taking this as 0.11, it is coming very much closer to 0. So I should be able to work out taking the value to be as good as a 0. Let me see if a solver can do this a little bit better. Error, I want to set it to 0 by changing this. Yeah, I got some better value through solver. Goalseek is not able to give me, so it is 0.1296. This is the one that has set the value to 0, which means somewhere I have got my R as 0.1296. Right, so so here I am getting my adjustment coefficient, and if I am doing it as a correction to 2 decimals, it would be somewhere around 0.13. So if I have to round it off to 2 decimals, if I have to round it up to 2 decimals, it's somewhere around 0.13. Okay. The same reinsurer also offers a proportional reinsurance with the same premium loading, such that reinsurer pays a proportion alpha of each claim. So there is an alpha of each claim. Now what is the expected claim now? We have already known that the expected, see the typical expected claim are 70% chance that 1 would be paid and 30% chance that 8 would be paid. On one single policy, the expected claim is somewhere around 3.1, and we have number of policies. Expected number of policies is lambda. So expected value of S is expected value of n times expected value of x. Expected value of x is 3.1, expected value of n is lambda. So on the original, this is the typical number of claims, expected claim amount. On this expected claim amount, a proportion alpha is what is being paid. Reinsurer pays a proportion alpha of each claim. So the expected claim payouts by the reinsurer are this much, and on the top of that he is charging a premium of 2.2 times, which is 120% loading. So overall it is becoming 2.2 times 3.1, right? So it is almost around 6.82 alpha lambda is the typical premium, or is the typical premium that the reinsurer will be charging. Right, in this case the reinsurer is charging 6.82 lambda. So show that the insurance company may either purchase excess of loss reinsurance with a retention M, or the proportional reinsurance with alpha equal to this much for the same premium. Now what was the premium in case of excess of loss reinsurance? We have already seen what was the premium that the reinsurer was paying, or the insurer was paying the reinsurer? It was around 0.66 lambda times 8 minus m. So these two should be equal because we are talking of the premium should be the same. So 6.82 alpha lambda is equal to this. So if I am taking out lambda, alpha is directly coming out to 0.66 by 6.82 times 8 minus m. Right, and probably if I have to simplify it, right, 66 by 682, if I am taking out 0.22 across, this is very much coming out to 3 by 20, 31 times 8 minus m. So we are able to get this particular number. So if alpha is set as 3 by 31 times 8 minus m, then whether we are going with a proportional reinsurance with a retention limit of m, excess of loss reinsurance with a retention limit of m, or a proportional reinsurance with alpha of this much, both of them would be costing the same amount of a premium. Then determine whether the adjustment coefficient with the proportional reinsurance is higher or lower than with the excess of loss reinsurance when m equal to 4. Now from here I should be able to know what is my alpha value for m equal to 4. It becomes 3 by 31 times 8 minus m, which is 4, which works out to 0.38. So when I am setting my retention level, the payout from the reinsurer's perspective, if the reinsurer is ready to pay 38.7, so the remaining is what is borne by the insurer. Now if I look at the mx, the moment generating function of r, from the insurer's perspective, e to the power of, when the claim is 1 with a probability of 0.7, the claim is 1, the insurer would be paying 1 minus of this, so which is 0.6129. 0.6129r, and with a 30% chance, when the claim is 8, he would be paying 8 times this, which is around 4.903r. This is the right hand side. Left hand side. The right hand side is going to become 1 plus CR. Now again C and R, they are not changing. So because the proportion that is being, the premium that is being charged and everything remain the same, so I'll still use the same 2.32 R, which we have used even in this case. Even in this case, whatever the right hand side, 4.96 minus the 0.66 times 4.66 times 8 minus m. So that is the same number I may have to use again here. So here if I go with the left hand side, it is 0.7 times. Now I have to identify a new R. Even let me take 0.1 itself because I want to compare. Left hand side will become e to the power of 0.6129 times R times 0.7 plus 0.3 times e to the power of 4.903 R. So which is working out to left hand side being equal to this, and from here I can work out my right hand side is 1 plus 2.32 times R. So right hand side is working out to this much, then error is very much working out to this number minus this number squared. So this I'll pass it on to solver to traditionally solve this expression for me, which will tell me that the new R should be somewhere around 0.095. Here the R is 0.129 and here the R is lesser. In the proportional reinsurance, the R is lesser. And probably when I'm talking about e to the power of minus R, going with the Lundberg's inequality, e to the power of minus R u, I mean u whatever is the initial limit that I am, the initial surplus that I am having, e to the power of minus r, here you will get a lesser e to the power of minus r and here it will be slightly a higher e to the power of minus r. So the adjustment coefficient, the higher and higher it is, I see that the probability of ruin will be much lesser. So here the adjustment coefficient is higher, so the probability of ruin is lesser. So if I have to really do a comparative analysis in terms of which of these methods is going to reduce the probability of ruin, I see that the excess of loss reinsurance can very well reduce the probability of ruin compared to that of the proportional reinsurance. Though the premium payment is the same in this case, the excess of loss reinsurance is going to reduce the probability of ruin in this entire perspective. Alright, so that's how this particular numerical needs to be looked at.